Hello, welcome you all in this lecture of heat and mass transfer, and this is lecture number 4 of this course. And today we are going to discuss the concept of heat generation. Okay, the heat generation is important in the derivation of general heat conduction equation. So so the objective of today's lecture is that the student should be able to identify the thermal conditions on the surface and express them mathematically as boundary and initial condition. The student should be able to solve one-dimensional heat conduction problem and obtain the temperature distributions within a medium and heat flux. And the student should be able to analyze one-dimensional heat conduction in solids that involve heat generation, evaluate heat conduction in solids with temperature dependent thermal conductivity. So all these are the objectives of our present class, and we are uh, going to discuss the concept of we are going to discuss the concept of heat generation. First we will start understand what is the meaning of heat generation, then we will use this heat generation in the steady state heat conduction equation. Okay, so as you can see these are there are some examples in our daily life where heat generation takes place. Okay, for example, electrical energy being converted to heat as at a rate of I square R. Okay, so we have seen that there are electrical heater, or there are some other electrical devices where which convert electrical energy into heat. Okay, as you have seen, the most common example of heat generation is the electrical heater. Okay, so that electrical heater itself generates heat. So the heat produced due to the electricity can be described as the heat generated by the system. Okay, heat generated by the system itself, and that is given as the I square R. Okay, so any system that produces heat apart from the heat is being transferred from one part of the body to the other part of the body, and then the heat can be generated within the body itself. Okay, so this is one example of heat being generated. Similarly, fuel elements of nuclear rods. Okay, so nuclear in the nuclear reactor, if you are considering nuclear reactor as a single body, so you can say that some heat is being generated inside that nuclear reactor. Okay, so the generation of heat inside the nuclear reactor is an example of heat generation within the body itself. Similarly, the chemical reactions, especially which are which are exothermic in nature. Exothermic reactions are those reactions where the heat is being generated, where heat is generated. Endothermic reaction, heat is absorbed. In endothermic reaction, heat is generated. So generation of heat in a exothermic reaction. Okay, so let's say that in a you can say in some system, or during a chemical reaction, or the if you consider the chemical reaction taking place inside let's say some instrument. In that instrument, if the heat is the heat generated, if that is the whole system, if you have considered the instrument as the whole system, then you can say that heat is being generated inside the body. Okay, so heat generation is a volumetric phenomena because it is generated inside the body. So generated heat is expressed in terms of volume. Okay, like for example, here heat generation can be expressed as watt per meter cube. Okay, similarly, or in British thermal unit, heat can be expressed in this format. Okay, similarly, the rate of heat generation in a medium may vary with time as well as position within the medium. Okay, so in a medium, if the heat is generated, it doesn't mean it will be continuous. It may be bit time dependent. Okay, bit time heat generation may increase or decrease, or it may vary. Okay, I mean increasing, decreasing, fluctuating heat generation, and within that medium, maybe in one position the heat generation is less, and in other position heat generation is more. Okay, for example, in the you can say, in the heating coils of an electric of an electric range as the result of generation of heat. Okay, so in this case, heat generation may be different from two different heat generation may be different, and between two places, and generally heat generation is given using this equation. Heat generation, total heat generation is given as the function of heat generation per unit volume, and the volume of the body itself. Okay, so heat generation E gen into dV integral V. So the total heat generated can be given as E dot gen and V. Okay, so this is how the heat is generated within the system, and this is the concept of heat generation within the body. Okay, so one of the examples is shown over here, that how the heat is how the heat is generated. Okay, so in order to size the compressor of a new refrigerator, it is desired to determine the rate of heat transfer from the kitchen or air into the refrigerated space through the walls, door, and the top and the bottom section of the refrigerator. In your analysis, would you treat this as a transient or steady state heat transfer problem? Also, would you consider the heat transfer to be one dimensional or multi-dimensional? Okay, so this is the problem, that if this kind of you can say, this is a refrigerator and a compressor has to be ordered. Okay, so whether we will consider the heat generation, I mean this problem can be considered or transient or steady state, how and we have to give whether the heat transfer is one dimensional or multi-dimensional. So okay, so this is the problem that we have. So the solution of this problem is that heat transfer process from the kitchen air to the refrigerated space is transient in nature, since the thermal condition in the kitchen and the refrigerator in general changes with time. However, we would analyze this problem as a steady state problem under the worst anticipated conditions. Okay, so under the worst anticipated conditions means that there will be lots of heat generated. Okay, in that condition we can consider this as a steady state problem for the simplification of our you can say study. Okay, so the anticipated highest temperature of the kitchen, okay, like we will design our refrigerator in such a way that what is the highest temperature inside the kitchen. This will be called the design condition. If the temperature is largely enough to keep the refrigerator the space at the desired temperature setting under the presumed worst condition, then it is large enough to do so under all condition by cycling on and off. So the heat transfer into the refrigerated space is three-dimensional in nature, since the heat will be entering through all six sides of the refrigerator. However, heat transfer through any wall or floor takes place in the direction normal to the surface. Thus, it can be analyzed as being one-dimensional. Therefore, this problem can be simplified greatly by considering the heat transfer to be one-dimensional at each of the four sides as well as to the top bottom sections, and then by adding the calculated values of heat transfer at each surface. Okay, so in this way this problem can be can be simplified as steady state problem with one dimensional heat conduction. Okay, so this is how the you can say the problem involving refrigerator heat transfer is solved. So again there is one more problem. This is a hair dryer, and the wattage of hair dryer is 1200 watt. Okay, so the problem is in this way: the resistance of wire 1200 watt hair dryer is 80 centimeter long and has a diameter of 0.3 centimeter. Determine the range of heat generation in the wire per unit volume in terms of watt per centimeter cube, and heat flux on the outer surface of the wire as a result of heat generation. So this is the problem. Okay, there is a hair dryer, and the you can say the power of the hair dryer is 1200 watt, and we have to find the rate of heat generation per unit volume, and also the heat flux on the outer surface of the wire as a result of this heat generation. Okay, so as you can see, the power consumed by the resistance of wire and dryer is already given to us, and the heat generation and the heat flux are to be determined. Okay, so the heat generation, as you can see, the heat is generated uniformly in the wire. This is the assumption we have to make, otherwise the problem will be difficult. The 1200 air dryer will convert electrical energy into heat in the wire at the rate of 1200 watt. 1200 watt. Therefore, the rate of heat generation in the resistance wire is equal to the power consumption of a resistance heater. Then the rate of heat generation in the wire per unit volume is determined by the dividing the total rate of heat generation by the volume of the wire. Okay, so this is the rate of heat generation. We have to find the rate of heat generation in terms of watt per centimeter square. So this is the total heat that it can generate. Okay, so this is the total heat can generated is basically 1200 watt. Okay, this is the amount of heat that this hair dryer can generate, and this is the volume, and we have to find the volume of the wire. Volume of the wire can be found from the diameter of the wire and from the length of the wire. Okay, so length of the wire is 80 centimeter and diameter is 0.03 centimeter. Okay, so the volume of the wire, if this is the wire and it has diameter d, and then you can see if this is the wire and the diameter of the wire is d, and this is the length of the wire. So the volume of the wire can be represented as pi by 4 into d square. In this way, pi by 4 into d square into length. Okay, this is the formula for finding the volume of a cylindrical device. Okay, if the length of the cylinder is L and D is the diameter, then this will be the volume of the you can see the cylinder, and the wires are basically of the cylindrical shape. So that is why this formula can be is used for finding the volume of the wire. Okay, now all the values are known to us, so we will put all the values, and since the values are in the centimeters, so the final value of the heat generated per unit volume in terms of centimeter cube comes out to be 212 watt per centimeter square. Similarly, we have to find out the heat flux. The heat flux is defined as the heat transfer rate per unit area. Heat transfer rate per unit area. Okay, now this is the amount of heat that can be generated. Okay, per unit time. Okay, 1200 watt. This is the amount of heat that it can produce per second, and then we will divide this with the area of the you can say wire. Okay, now there are two areas of the wire. One area is this one. Okay, surface area, and this is the cross sectional area. Okay, now the heat now you will confuse that which area we should take. Okay, now remember that most of the heat that is being generated by this wire will be transferred from the surface. Okay, will be transferred from the surface. This is how the heat will be transferred from the surface. Heat generation from this surface, as you can see, or from this part to this part will be negligible, because the length of the wire is very large compared with the diameter. So we will consider this only as the heat transfer from this surface only. Okay, so we will take this area only. Okay, now the surface area is given area of this surface you can see is given as a equal to the perimeter of the perimeter into length. Okay, so this is equal to pi into d into L, pi d and L. So in this way, the area can be calculated. Area of this surface can be, sorry, area of this surface can be calculated. Okay, we are using this area because most of the heat transfer will take, majority of the heat transfer will take from this area only. That is why this area has been used, pi into d into L. That is, we put the values here and we will get the final answer. Okay, so this is the this is how the heat flux is obtained. Now heat flux obtained is 15.9 watt per centimeter square. Okay, this is the, so our problem is solved. The next thing is that how to derive the heat conduction equation. Okay, we have discussed the heat transfer, one dimensional heat transfer, two dimensional heat transfer, and three dimensional heat transfer. Now we have considered the heat generation within the body. Okay, heat generation within the body. So the heat conduction will be the combination of heat transfer from one surface to other surface of the body plus the heat generated by the body itself. Okay, so if we take these two things, then we can start the derivation of the one dimensional heat conduction equation. Okay, now let us consider the heat conduction through a large plane wall, such that the wall of the house, the glass of the single pane window, the metal plate at the bottom of the pressing iron, a cast iron steam pipe, a cylindrical nuclear fuel element, and electrical wire, the wall of a spherical container or a spherical metal ball that is being quenched or tempered. Okay, now consider all these cases, okay, one by one, and think about these. Okay, like a large plane wall with wall, I mean through a large plane wall as the wall of a house. So the you consider the wall of your house. Okay, so what is this? This can be treated as one dimensional steady state, one dimensional heat conduction equation. Why? Because the thickness of the wall is very small compared to the other two dimensions. Okay, so that is why we can consider this problem as a one dimensional problem. Similarly, the glass of your window pane, okay, single pane window, again the thickness is very small compared with the other two dimensions. That is why again this heat transfer problem from this single pane window can be considered as a single or one dimensional heat transfer problem. Okay, so all these problems that are shown over here can be treated as a one dimensional, you can say one dimensional problem. Okay, and heat conduction in these and many other geometries can be approximated as being one dimensional, since heat conduction through these geometries is dominant in one direction and negligible in other directions. Next, we will develop one dimensional heat conduction equation in rectangular, cylindrical, and spherical coordinate, as we have discussed in our previous lecture. Till now we are discussing the basics of the heat conduction equation, how to derive the heat conduction equation, and what factor we will be considering in the heat conduction equation. Okay, so when we are dealing with conduction consists of two things. One is the heat transfer by conduction from one surface to other surface. Okay, and another thing is the heat generated within this body. Okay, if we have a body and heat, so two things can happen. Heat may be transferred from one end to another end, and heat may be generated within the body. Okay, so these two things should be considered simultaneously for the one dimensional heat conduction equation, for the derivation of one dimensional heat conduction equation. So this is the you can say this is our problem. Now let us consider this you can say this block. Okay, and within this block, let us consider a small volume element whose volume is dv, and the thickness of that volume is let's say this is equal to dx. Okay, so within this small volume of thickness dx, the heat is transferred from this plane to this plane. Okay, from this heat is transferred from this side, enters from this side and leaves from this side. Okay, let us say that heat entered in this plane is qx, and heat that left is qx plus dx in terms of the dimension. Okay, so and some heat is being generated within this volume element. As you can see here, some heat is being generated. Okay, so the total heat transfer will be the you can say heat transfer as well as the heat generated. Okay, that is why from the first law of thermodynamics, we apply the first law of thermodynamics on this small volume. We can say that rate of heat conduction at x minus rate of heat conduction at x plus delta x. Why we have writing this? Because heat is entering into this small volume. If we consider this small volume as our system. Okay, so from the first law of, from the laws of thermodynamics, we know that heat entering in the system is taken as positive quantity, while heat leaving the system is taken as negative quantity. Okay, so the rate of heat conduction at x is positive, and it is negative, qx plus delta x is negative. That is why these two quantities are subtracted from each other. Then plus the rate of heat generated inside the element, rate of heat generated inside the element will be equal to the rate of change of energy content of the element. Okay, rate of change of the energy content of this element. Okay, so if this is the very simple case of you can say first law of thermodynamics, where we calculate what is the change of the energy of the system. Okay, so how we do? We say that the heat entering heat and work entering, heat is I mean heat supplied and leaving the system, plus work done by the system or work done on the system is equal to the change in the energy content of the system. Okay, so this is the same thing is written here. Okay, so this quantity will reflect the change in the energy content of the system due to the heat conduction from one surface to another surface, and this quantity will represent the change of rate of you can say change of energy content of the system, because some heat is being generated there. Okay, so if we add these two heats, we will get the total you can say change in the energy content of the system. Okay, since the energy is continuously changing, the energy content is continuously changing, and heat is being continuously being transferred, and heat is continuously being generated. So we are writing all these things in terms of rate. Okay, with respect to time. Okay, so so the rate of heat conduction at x equal to qx, then the rate of heat conduction is qx plus delta x, then this is the rate of heat generated written over here, and this is the rate of change of energy content of the element. Okay, so all these equations are written over here. Now further you can we can simplify I mean we can start simplifying or elaborate this equation like this, that let's say that the energy content to what is the change of the energy content, or this value. Okay, this value of the system, what is the total energy content of the system. Okay, so this can be described as energy content at t plus delta t time, and the energy content at time t. Okay, so this can be written as m into c into t plus delta t minus t. Okay, t is t subscript small t. Okay, c is the heat capacity and m is the mass of the element. Okay, so it can be written as rho ca delta x into t plus delta t minus tt. Okay, so rho is the density of the element. Okay, if the density is known, then we can express this in terms of rho into you can say rho is the density, and a delta x, here a delta x is the volume of the element. Okay, volume of the element. So rho into volume, density into volume is mass. Okay. Similarly, this is the change in the energy content of the element. Now let us find the find the energy generated within this element. Energy generated within the element can be given as E generation into V volume of the element. Okay, volume of the element. E gen is the heat generated per unit volume. Okay, small E gen. And this small E gen into volume of the element is A into delta x. Okay, now put these values. Okay, put the value of element over here, and the E generation of the within the element over here. So we get Q minus qx minus q x plus delta x, and E generation A plus delta x, and rho C A delta x, and this quantity. Okay, so we have put this quantity, this is the quantity we have put over here. Okay, and this is the quantity we have put over here. Okay, we have put the quantities within this equation. Now divide this equation by A delta x. Okay, divide this equation by A into delta x. Okay, so we have divided this equation. Now after before dividing, we rearrange this part of the equation. This part of the equation we are rearranging, and how we are rearranging, we are putting in this way. Okay, we are putting in this way, like this. Okay, qx plus delta x minus qx, so minus will come out, out from here. Okay, and then after dividing this equation by a upon a into delta x, so what will happen, that a will be we have taken a out of this bracket and put delta x within this bracket. Okay, so the within this bracket the quantity will be qx plus delta x minus qx upon delta x plus E generation, because since we have divided a by a delta x, so a delta x divided by a delta x will be 1. So E generation, I mean the heat per unit volume will be equal to rho C Ti plus delta T minus T at time T plus delta T minus temperature at point delta at point T at time T divided by delta T. Okay, so this is the this delta T is basically the time. Okay, this delta T is the time. Okay, capital T is the temperature and small t is the time. Okay, so don't confuse with small t and capital T. Capital T is temperature and small t is the time. Okay, taking taking the limit at x tending to 0 and delta t tending to 0, so we can write this equation in the partial differential form. Okay, 1 upon x del over del x ka del t over del x. Okay, so in this way we can rewrite this equation. Okay, why what is this quantity, qx plus delta x minus qx upon delta x, this quantity, this is the quantity that is called the Fourier's law, that has come from the Fourier's law. So in this place, in I mean qx plus delta x minus qx, we can write as ka del t over del x. Okay, so this is actually del q. Okay, so that is why it is written 1 upon n del x into kx ka into del t over del x plus E gen equal to rho c del t over del t. Again here you can say that why we have not written dt over dx. Okay, we have written this equation in the form of partial differential equation, because the heat transfer here depends on not just x but also on the time. Okay, that is why all the quantities are written in terms of partial differential equation. This is how we have taken the limits from here to here, limit extending to 0. So this quantity will become del t del q dot over dx, del over del x, keep it out. So del q equal to minus kx del t over dx from the Fourier's law, and this is the quantity that we have put over here. Okay, so this is how the how we achieved this part of the equation. So we can for this is how we can again write written this equation over here, that del over del x and del over del x k del t over del x E generation equal to rho c del t over del x. Okay, in many material k is also variable. K is called the thermal conductivity. Okay, so the thermal conductivity is also variable. So in order to make you can say in order to incorporate a variable thermal conductivity, this quantity is written within this bracket. Okay, so for if the thermal conductivity is variable, this equation will be utilized. If the thermal conductivity is constant, so what will happen, that this quantity will come out of this bracket. Okay, and we can divide this by k throughout the whole equation. So what will happen, that del over del x will become equal to del 2 over del t upon del x square. And since k has come out of this bracket, and after dividing, what will happen, that k will be divided over here if it is constant. Okay, so it will become egen upon key equal to 1 upon alpha. Alpha is equal to rho c. Now here you can see this new quantity is introduced. This is equal, this is called the this is basically nothing but k upon rho c. Okay, k upon rho and c. Okay, k upon rho c, where c is the specific heat of the material, rho is the density of the material, and k is called the thermal conductivity. Okay, and this alpha is known as the thermal diffusivity. This alpha is known as the thermal diffusivity. Okay, so if the steady state exists, okay, what will happen if the steady state exists? So what will happen, that this quantity will be 0. Okay, if the steady state exists, what will happen, that this quantity is 0 because the things are not changing with respect to the time. Okay, so del t over del t, small del t, will be equal to 0. So what will happen, that this equation will transform into this form. Okay, and when there is no heat generation, then this equation will be further I mean when this sorry I mean when there is no heat generation, so what will happen, that this equation will transform into this way. Okay, in this equation. Okay, again this equation represents the heat conduction, transient heat conduction. Okay, and if let us say that this is the in this equation, if this is the steady state, then what will happen, that this equation will transform into this equation, that is del 2 d2t over dx square equal to 0. Here you can see that it is written d2t upon dx square. Okay, del is now removed because since the uh, 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 the heat conduction has become steady. Now the heat conduction depends only on one quantity, that is the position. Okay, that is why this will be the exact differential. This has become now the exact differential. That is why we have written d2d over dx square. Okay, so we have these are the three conditions. Steady state means del t over dx will be 0, so this equation will come out. In the transient state, this equation will come out, and when the steady state and with no heat generation, then this equation will be will be obtained. Okay, so in this way we obtain the general heat conduction equation through a plane wall. Again, for example, in one dimensional, we have already discussed this part of the equation, that the simplification of one dimensional, as you can see from here, that no heat generation and steady state, so these quantities will become 0, and we obtain this value. Okay, we obtain this values, the simplification of one dimensional heat conduction equation in a plane wall for the case of constant conductivity of steady conduction with no heat generation. Okay, so this is the steady state one dimensional. Next is the uh, mm, heat conduction equation in the long cylinder. Again the heat conduction equation will be derived in the similar way that it was derived for the plane wall. Only change will happen, that heat conduction at R and heat conduction at R plus R. Okay, since it is a cylinder, so in the cylindrical coordinate R and R, theta and L will be the three coordinate, or I mean coordinate is expressed in terms of R, theta and L. Okay, so since it is a one dimensional, we are deriving only in the one dimension. So what will happen, that most of the you can say the heat transferred in the cylinder takes place along the radial direction. Okay, along the radius of the cylinder. So only the heat transfer we will be concerned here will be the heat transfer along the radial direction. Okay, so again the equation will be written like this. we will assume a element or a cylindrical element within this cylinder, whose you can say whose thickness will be delta r, and the radius will be r. Okay, so radius will be r, so outer radius of the cylinder will become r plus delta r. Okay, so in the similar fashion, qr, I mean q entering in this cylindrical element and leaving, qr plus delta r is the element leaving the cylinder. Okay, so qr minus qr plus delta r plus E generation within the element and delta E of the element. So delta E will be, I mean the change in the energy content of the element is given by this equation that we have earlier discussed. Here only change will be the volume. Okay, volume is now given as A into delta R. Okay, A into delta R. A is the area, A is the you can say surface area of the element, and delta R you can say is the thickness. Okay, so thickness of the element. Okay, so in this way the volume will be calculated, the volume of the cylindrical element will be calculated. So in the similar fashion, as you can see, the energy generated within the element has been calculated, heat generated within the element has been calculated. So putting these values in the equation that we have earlier discussed, we get this equation, and after dividing this equation by a upon a into delta r. Okay, a into delta r, so what will happen, that we get this equation. So taking limits as r tending to 0, delta t tending to 0 will yield this equation, and this is how this part of the equation, is obtained. This is how the first we will take the limits, and then we will get this part of the equation. Okay, so this is how the you can say heat generation in a long heat conduction in a long cylinder takes place. This is the heat conduction equation for a long cylinder. Okay, so this is the equation that we obtained. Okay, if the conductivity is variable, then it is represented in this form for a long cylinder. This is the general equation in one dimension for a long cylinder. Okay, and if the thermal conductivity is constant, so the thermal conductivity will come out of this bracket, and it is we can divide this using this thermal conductivity in the whole equation. So what will happen, that here we will get the alpha is the thermal diffusivity, and it is written as K upon rho Cp. Okay, then if this is the general equation. Okay, this is the general equation. Now in this general equation, if this is the steady state condition, so what will happen, that this part of the equation will become 0. Okay, so this part of the equation del over del T will become 0. So this equation will be obtained if it is a transient and no heat generation equation. If it is a transient case and no heat generation is taking place, then the above equation will be transformed like this. And if it is a steady state with no heat generation, then we will obtain this equation. Okay, so this is how this equation is obtained. And this is again the equation is written in the simple form, that two equivalent form of the differential equation of one dimensional steady state conduction in a cylinder with no heat generation. Okay, so this is the form that we obtain. After further expanding this form, I mean after further expanding this equation, we obtain this equation. Okay, r del 2 d2t upon dr square plus dt over dr. This is the another form of the same equation. Only thing is that this time we have expanded this equation. Now derive the heat conduction equation in a sphere. Okay, now let us derive this equation for a sphere. Okay, so again for the sphere, the general equation will look like this. Okay, the general equation in one dimension will look like this. Okay, again we have taken a small spherical element for the for deriving this equation. Okay, again in this for this we don't need to derive the whole equation. I'm simply we simply have to know how the equation of the state conduction equation looks like. Okay, so if the conductivity is constant, the equation will further change into this form. Okay, again this is a general equation. Only difference between the two equation is that the conductivity in the latter one is constant. Okay, then again same in the same way, if it is a steady state equation, then this equation will be obtained in the transient and with no heat generation be obtained this equation. And if this is a steady state with no heat generation, then this equation will be obtained: d over dr r square dt over dr equal to 0. And if we further expand this equation, we will get this equation. Okay, r del 2t over del r square plus 2 dt over dr. Again I am repeating it again: r dt over dr square plus 2 dt over dr equal to 0. Okay, so in this way this is another form of the same these two are the same equation. Only thing is that this equation has been further expanded only. So today what we learned, we derived, we did the heat transfer analysis. Okay, and how what is the meaning of heat generation, this is what we learned today, and how the heat generation is important for the derivation of the one-dimensional heat conduction equation. Similarly, heat conduction equation can be derived by performing an energy balance on a differential volume element. This is what we learned, and this is the summary of the today's lecture. So these are some of the review question. How does the heat transfer differ from the steady heat transfer? Okay, so what is the difference between heat transient and steady one dimension? What is the difference between one dimensional heat transfer and two dimensional heat transfer? And what is whether heat transfer is a scalar quantity or a vector quantity? Thank you. Okay, so these are the references from where the material is taken, and you can refer to these books. Thank you for listening to this lecture. Thank you all.